Hello. This lecture is called Types of Solution Sets. So let's remember, so far what we've been doing is that given a linear system, we express the system in matrix vector form. That is a rectangular array of numbers we're calling a matrix, which stores the coefficients, all these numbers multiplying the variables, and we form the augmented matrix. Now the augmented matrix is then row reduced. These operations we learn and the specific shape of a matrix called the RREF, the acronym for reduced row echelon form. Well, that is going to be the key in formulating not just one, but all possible solutions that a linear system may have. And that's the importance on determining, on calculating the set of solutions, or the so-called solution set, which is the subject of this lecture. A linear system of equations is either going to have solutions or is not going to have solutions. If the system has no solutions, then we call that system inconsistent. When there is at least one solution, and so here's the thing: like the system may have at least one solution, it may have one and only one solution, or it may have multiple, infinitely many solutions. So in the case in which there is at least one solution, we would term that system to be called consistent. We consider this matrix now. It has 5 rows and columns. This matrix is in RREF. Clearly here we have 4 non-zero rows. We count the number of leading ones, or the number of pivot columns. The indices where these leading ones, or these pivot columns are in column 1, column 3, column 4, and column 7. So those would be the indices we would store in the set capital D. And the other indices here labeled with F are column 2, column 5, column 6, column 8, and column 9. So the set capital D is 1, 3, 4, and 7, and here's the set capital F. So these sets of indices, one important thing to notice is that they are considered a partition of the indices of the matrix. And excuse me, this partition is mutually exclusive. That means there is no intersection. They have nothing in common. So either some indices are in one set, some indices are to either be in one set D, or they will be in one set F, but there are no indices that are in both sets at the same time. So the columns are partitioned in this way. The number R, this number of leading ones or pivot columns, is extremely important. This will be something that certainly will resonate throughout this course. But very importantly, this number is calculated from the RREF, and it's due to the importance of this number of leading ones that is extremely first priority to make sure that indeed a matrix is in the RREF. There are no missing steps that to reassure that it is being reduced. So this is part of the information we have said. For each leading one, we have a pivot column, so R is also the number of pivot columns. So R is the number of non-zero rows in the RREF, the number of leading ones, and the number of pivot columns. So here is an example with 4 equations, 7 variables. Okay, so in general, the coefficient matrix is assumed to be m by n. In this case, we're talking about a coefficient matrix that is 4 by 7. The augmented matrix, however, would be 4 by 8. We augment the coefficient matrix, throwing or stacking as a last column the column formed by the constants. This is so-called the vector of constants. Then we have a 4 by 7 matrix. And part of what I'm not displaying here, and I am leaving this up to you, is the calculations involved in forming the augmented matrix and row reducing the augmented matrix. So this is a good time for you to pause, to translate this system into vector matrix form, create the augmented matrix, and do all the row operations required to compute the RREF of that augmented matrix. So in this case, the augmented matrix has this RREF. We see that the number of non-zero rows, or the number of pivot columns, is 3, and the sets storing indices of pivot columns is D, or containing 1, 3, and 4, and then capital F containing all the other indices 2, 5, 6, 7, and 8. Okay, so these steps seem rather simple. They are simple, and they rely heavily on the calculation, right? This relies on the calculation of RREF, reduced row echelon form. Now, what we're going to do next is to think of the variables. And also we're going to use the partition of the information we have on those sets of indices. We're going to use that to our advantage. So we're going to think of a variable that has an index. Don't get distracted here. D sub I, that is, there is D sub 1, there is D sub 2, and so on. Let's go maybe back one slide. Here we have D sub 1, D sub 2, and D sub 3. Well, each of those is simply 1, 3, and 4. So this is a way of denoting the indices on that particular set. And what we want to do is to now write the variables with indices on that other set, F. Okay, so we're going to split the variables into 2 groups. And in particular, those variables corresponding to indices on the D set are going to be called dependent variables. And we're going to write them as, we're going to write the dependent variables in terms of the other variables with indices on the F set. Okay, so this will be clear in just a minute. So, for example, the first index in D is 1, so x1 is a dependent variable, and x1 can be written in terms of variables that are in the other set. So this is, of course, information that comes from this first row in the RREF. Remember, this is a row of an augmented matrix. The last column denotes the number that's on the other side of the equal sign, and this reads so that first row of the RREF would, if we translate that into the corresponding system of linear equations, that first row tells us that we have one x1 plus 4 x2 plus 0 x3 plus 0 x4 plus 2 x5 plus 1 x6 minus 3x7, and this equals 4. We have to remember that that last column is made of the vector of constants. So from this expression, we can solve for x1. Okay, we can solve for x1, and by solving for x1 in this expression, then you can easily see how it is possible to express x1 in terms of variables that have indices on that set that we're calling capital F. So in this case, those are x2, x5, x6, and x7. Now, for the next index on the set D, the next index would be D sub 2, which in this case is the index number 3. So doing the same, reading from the second row in the RREF, we can solve for x3 as this expression and find that x3 can be written as an expression that involves x5, x6, and x7. All of those indices are in that capital set and in the set capital F, and the same can be done for x4. So x4 here expressed in terms of x5, x6, and x7. So each element of the set F is the index of a variable, with the exception of the last number there, 8. 8 corresponds to the column that was kind of artificial. We created this matrix by augmenting the columns of the coefficient matrix. So always the last number in this set F is going to be ignored because it doesn't correspond to an index of a variable. So we refer to x2, x5, x6, and x7 as the free variables. So this is where we're introducing terminology to dub the variables into two groups. And so we're partitioning these sets D and F partition the indices, and precisely that partition allows us now to partition or divide the variables into a group that is called free variables. It's called free, and therefore here capital F, and also another group of variables that's going to be called dependent. Okay, the free variables are allowed to assume any possible combination of values that they can take, and these free variables are used in the definition of the dependent variables. So we refer to those in this example, x1, x3, and x4 as the dependent variables. They depend on the free variables. I give you a couple of seconds so you can read this, but the important thing is that we would like to express the solution set. The solution set is going to be something expressed in this form. In this case, what we do always first is we list the vector, and then we divide that with a bar here, and then we write some information. In general, this vector would be x1, x2, all the way through x7. But instead of writing x1, instead of writing x3 and writing x4, we're going to write the expressions that we had found for those in terms of the free variables. So that so-called solution set is something that looks like this. You can see this expression here corresponds to x1, and similar for this expression, which corresponds to x3, and the next expression corresponds to x4. So we have this vector with 7 entries, and the so-called free variables are listed after the bar, and it is indicated that they can take any value on the complex plane. They are assumed to be complex numbers. And so this is what we will consider the solution set for this example.